The Vector Quantization Storage Engine provides compressed storage and approximate nearest neighbor retrieval for high-dimensional embedding vectors. The system employs product quantization to reduce memory footprint, while maintaining acceptable precision for similarity search operations. This document describes the initialization parameters, internal representation formats, and query execution pathways for the current stable release. Initialization requires specification of the dimensionality parameter, subspace count, and bits per subspace assignment. The dimensionality must be a positive integer. Typical values range from 64 to 2048. Subspace count determines the factorization granularity and directly influences both compression ratio and computational cost during encoding. This parameter must divide evenly into dimensionality with no remainder. The bits per subspace parameter controls the codebook size for each subspace. Valid values are integers from 4 to 16, corresponding to codebook sizes from 16 to 65,536 centroids per subspace. Lower values reduce storage overhead but increase quantization error. The total compressed size per vector equals the product of subspace count and bits per subspace, rounded to the nearest byte boundary. The encoding process partitions the input vector into contiguous subspaces of equal dimension. Each subspace is independently encoded using k-means clustering. The k-means procedure initializes centroids using k-means ++ selection and iterates until centroid shifts fall below a convergence threshold of 1e4. Encoding assigns each subspace to its nearest centroid, storing only the centroid index. Training data collection occurs during the initialization phase. The system accepts vectors through a streaming interface until the internal training buffer reaches capacity, defaulting to 262,144 vectors. Once capacity is met, training commences without additional configuration. The training process reads vectors sequentially and maintains running statistics for centroid computation. Training completes regardless of total vector count processed. Distance computation during retrieval employs the Euclidean metric in the original space. The system pre-computes squared distances from all query subspaces to all codebook centroids, storing intermediate results in a lookup table. This table enables rapid distance estimation without decompressing query vectors or stored vectors. Lookup table computation scales linearly with subspace count and codebook size. The approximate distance formula sums subspace-level distances computed from the lookup table. Given a query and a stored vector, the approximate distance is the sum of lookup table entries corresponding to query centroid indices and stored vector centroid indices. This computation avoids accessing the original vectors, reducing latency and memory bandwidth requirements substantially compared to exact similarity computation. Retrieval operations accept a query vector and a result limit parameter. The system constructs the lookup table, iterates through all stored vectors computing approximate distances, and maintains a result set of the top k candidates. The algorithm performs a linear scan of all encoded vectors. No index acceleration structures are utilized in the standard retrieval path. Result ordering follows ascending distance values. Memory layout for encoded vectors follows a columnar format for cache efficiency. Each subspace's centroid indices are stored contiguously in memory. This layout enables perfect-friendly sequential access patterns during retrieval. The bit packing mechanism stores multiple centroid indices within single bytes when bits per subspace is less than 8. Byte alignment is maintained for retrieval performance. Batch encoding operations accept multiple input vectors simultaneously. The batch size parameter defaults to 4096 vectors. Larger batches improve throughput by amortizing centroid lookup overhead. Encoding processes vectors in order, assigning each vector to the nearest centroid in each subspace independently. Batch processing produces encoded vectors in the same input order without reordering or buffering delays. The centroid table stores all trained codebook centroids in a dense array format. Total storage is subspace count multiplied by codebook size multiplied by dimensionality divided by subspace count multiplied by 4 bytes per floating point value. Access patterns during retrieval are random due to varying centroid assignments. Prefetching provides minimal benefit. Centroid table size is fixed after training completion. Precision degradation from quantization is quantifiable through reconstruction error matrix. Mean squared error between original and reconstructed vectors scales inversely with bits per subspace. For typical configurations, reconstruction error remains below 5% of the original vector norm. Recall at specific distance thresholds degrades minimally for well-separated clusters in the original space. Adaptive centroid refinement is available through incremental training mode. This mode accepts new vectors after initial training and adjusts centroids to minimize reconstruction error on the expanded dataset. Refinement iterations increase centroid quality at the cost of computational overhead. Refinement is optional and disabled by default. Enabling requires explicit configuration parameter modification. Thread safety is not guaranteed in the current implementation. Concurrent encoding and retrieval operations on the same quantizer instance produce undefined behavior. External synchronization using locks or mutexes is required for multi-threaded applications. Read-only operations on a completed quantizer are safe to execute concurrently after training completes and no further centroid refinement is requested. Serialization of trained quantizers is supported through a binary format encoding centroids and configuration parameters. The format includes a header section containing dimensionality, subspace count, and bits per subspace values. Centroid data follows immediately in row major order. Deserialization reconstructs the quantizer state completely, allowing trained models to be persisted and loaded without retraining. Performance characteristics depend primarily on vector dimensionality and dataset size. Encoding latency scales linearly with dimensionality. Retrieval latency is dominated by linear scan cost, scaling with total stored vector count. Memory consumption is dominated by the encoded vector storage and centroid tables. For datasets exceeding 100 million vectors, external indexing structures such as locality-sensitive hashing are recommended to reduce retrieval latency.